Good morning, students. Yesterday, we have studied about the design of primary sedimentation tank. I thought I can give some of the important concepts related to the design of primary sedimentation tank. Last class I have explained about the type 1 settling and type 2 settling. The type 1 settling is related to the discrete particle settling, whereas the type 2 is related to the flocculent particles. That means during the process of sedimentation, the size, shape, then settling velocity of the particles will vary. Okay, whereas in case of discrete particle settling, then there is no change in size and the shape of the particles. Okay, here just you can see the design of like how to calculate the settling velocity of discrete particles. The discrete particles in dilute suspension. The dilute suspension is, that means you have a huge quantity of water with a very less amount of solids. Okay, there you can expect a type 1 settling. That means the settling of the individual particles will not interfere with settling of the other particles. If the particle is suspended in water, it initially has two forces acting upon it. One is the gravitational force, another one is the buoyant force. Okay, as you all know that the gravitational force, okay, will act in the downward direction, whereas the buoyant force will act in the upward direction. The buoyant force, gravitational force is like Fg, that is equal to rho p into G into Vp, whereas rho p is the density of the particle, and then Vp is the volume of the particle. And then another one is the buoyant force. The buoyant force is like rho W into G into Vp. Okay, then here rho W is the density of the water, Vp is the volume of the particle. Then if rho P is equal to, that means the density of the particle is equal to density of water, there is no net force, then there is no movement of the solid particles, or that there is no downward movement of the solid particles. If rho P is greater than rho W, maybe you can expect there is a net force, okay, that is acting in the downward direction. Okay, that is the F net. F net is rho P minus rho W into G into Vp. Then once motion has been initiated, okay, the third force, that is called as the drag, maybe it is called as the drag force, or this is mainly due to the viscous friction that may act on the fluid, that may act on the particle. Okay, this is the water. Okay, assume that this is the water. Okay, this is a particle. Initially there is two forces, one is the gravitational force, another one is the buoyant force. Then you will get the net force. The net force will take the particles to the downward direction. Once the motion is initiated, then there is a third force called drag force that will act in the opposite direction. That means initially you have an acceleration, but because of the drag force, there is a decrease in the acceleration, and then particle will reach the constant settling velocity after certain time period. Okay, that is called as the terminal settling velocity. Okay, now you can see here the drag force is Fd is equal to Fd is the drag force. This is equal to Cd, that is the coefficient of drag, and then Ap is the area of cross-sectional area of the particle, rho W into V square divided by 2. Here this V square is the settling, it is called as the velocity of the particle, and then Ap is the cross-sectional area of the particle, and then coefficient of drag. It depends upon the nature of the flow. Sometimes the flow may be the laminar, sometimes the flow may be the turbulent or transition flow. Therefore, the CD value depends on the like the nature of the flow. It depends on the Reynolds number. And then third force, that is the drag force. Then after some time, then the acceleration will come down. That means that when drag force is equal to the net force, then maybe that acceleration may be stopped, and then it will reach the constant velocity, that is called as the settling velocity. Is it clear, students?
Yes, ma'am.
Yeah. Then rho S minus rho W into G into VP is equal to CD AP rho W into, this may be called as instead of V square by 2, okay, that is V may be changed as T, the T is called as the terminal settling velocity, terminal settling velocity. This is important, okay, how to calculate the terminal settling velocity of the particle. Okay, the terminal settling velocity is 4 by Vt square is equal to 4 by 3 G into rho P minus rho W into D divided by CD into rho W. For the laminar flow, generally in water treatment systems, we used to expect the laminar flow. Therefore, the CD value is equal to 24 divided by RE. Okay, RE is the Reynolds number. You can use the Reynolds number this formula like pi into Vs into rho W into D divided by mu for the calculation of the Reynolds number. Okay, after substituting the Reynolds number in the CD value, and then finally this equation, the terminal settling equation is as like G into rho P minus rho W into D square divided by 18 mu. Please remember this equation. This is the equation generally we used to use to calculate the terminal settling velocity of the discrete particles. Is it clear?
Yes, ma'am.
Yeah. Now coming to the concept of like how the particles are like settling at the bottom, they have carried out a small batch study. Okay, that is called as the in the settling column. Okay, they have constructed a settling column maybe with a 3 meter height. Okay, initially this is the settling column. Settling column at the bottom you have a provision for the sled settling, and then this is a sampling port. Okay, they have just considered the like the, it is not a continuous process, it is a batch. That means they have admitted water into the settling column. Okay, then assume that initially the particles, okay, this is the height is at 0. Okay, this is the height is at 0. The particles initially at the height is at 0. Okay, then it may take time t0 to reach the bottom. Okay, for the that is okay t0. I can write here. Suppose the particle is just at the surface at a time equal to 0 and its settling velocity, okay, it's maybe we can say average settling velocity is such that it arrives the sampling port maybe at a time t equal to t0. Therefore, based on the height as well as the t0, we can calculate what will be the average settling velocity. Okay, the average settling velocity is at 0 by t0. Suppose some other particle, it is not at the height z0, it is at the height zp, it is at the height zp, that will also reach the bottom at time t equal to t0. Okay, assume that the particle, another particle, okay, that is at a height zp, because you are just keeping the water in the settling column. Therefore, the particle may be distributed throughout the depth of the column. Therefore, initially we have considered the particle at a height z0. It takes time t0 to reach the bottom. With that, we have calculated, because this is the worst condition, no? The particle may be there at the top. Then it may take some time to reach the bottom. Therefore, that is considered as the V0, average settling velocity. Now, imagine that one more particle that is at the height ZP, that particle also will reach the bottom, okay, at the same time period t0. Corresponding to this, the velocity may be Vp. Therefore, Vp is distance traveled by time of travel as t0. Now, by considering this equations, this may be 1, this may be 2, then we can say that t0 is equal to z0 by v0, and then because the t0 is same for both the cases, we can say that z0 by v0 is equal to zp by vp, or we can rearrange this equation as vp by v0 is equal to zp by z0. Now, based on this concept, they have generalized 3 observations. The first observation is any particle that is having the diameter greater than or equal to D0, because D0 is the worst case. That should be at the top position. Okay. Therefore, any particle that is having the diameter greater than D0. Okay. If the diameter is greater than D0, definitely having the settling velocity greater than V0 will arrive or pass the sampling port at the time T0. Is it clear, students? First point, first observation.
Yes, ma'am.
Yeah, actually, what you have to do is the first is you have to calculate V0, and then after calculating the okay, this is a settling column. Based on the settling column and time of travel, we can easily calculate what will be the V0. Now you have one reading with V0. Now use the terminal settling velocity formula. Terminal settling velocity formula that we have discussed in the previous thing is that it is equal to G into rho P minus rho W into D square divided by 18 mu. Now calculate the VT. If VT is greater than V0, okay, definitely it will reach the bottom maybe prior to T0. Is it clear?
Yes, ma'am.
Yeah, that is the meaning for the first point, first observation. Then the second observation is if Vt is less than V0, if Vt is less than V0, this also will reach the bottom. This particle also will reach the bottom if the particle enters at the height Zp. If the particles enters at the height Zp means this particle also will be removed at a time T0. Is it clear? If the particles with a velocity less than V0, if it starts from Z0, definitely it will not reach the bottom. Yes or no? Will not reach the bottom. Okay, please understand, will not reach the bottom. I have explained three things. One is if the particle is having settling velocity greater than V0, terminal settling velocity greater than V0, definitely it will reach the bottom of the settling zone at the time prior to the T0. Okay. Then if the particles having settling velocity less than V0, but if it enters at the height Zp, also will reach the bottom at T0. That is the second observation. Third observation, if the particles, okay, having settling velocity less than V0, but at the same time, the position of the particle is Z0, then definitely, then this particle having like other than like it should be removed in the ratio of Vp by V0 into Zp by Z0. It is any particles that is having velocity less than V0. It is not exactly Z0, below the height of Z0. Okay, we have considered two things. One is Z0, another one is Zp. Okay, other than this, okay, other than this, that means somewhere between here. That means generally the suspensions are like or we can say that the particles are completely suspended in the liquid. It may be distributed throughout the depth of the column. Okay, if it falls with the first two conditions, that may reach the bottom at the time T0. If it falls between maybe Z0 to Zp, then that particles may be removed with the ratio of Vp by V0 as Zp by Z0. If you have any clarifications, then I can explain to you, then I will move to the next one. Students, any doubts? They are talking about complete removal of the particle. That means complete removal means it may settle at the bottom of your chamber. If you are taking the liquid at the sample port, that is free from suspended solids. students, or you can say because this is a bad study, we can say that passing also they have used the word, no, the passing. Okay, like here maybe they have used arrive or passing the sampling port. Arrive or passing the sampling port. That means the particle started movement from the top and then it will move, then it may come out. Okay, that means it is reaching the settling zone. It is reaching the settling zone. With that, what they are saying is, if it is exactly equal to V0, that may be, or more than V0, it may be completely removed or completely. That means the particle may pass the sampling port. It reaches the bottom. Okay. Then if it is at some other height, that is with the ZP, that will also reach the sampling port at time t equal to 0. But the position should be with the ZP. Okay. If it is between Z0 to ZP, okay, or in some other locations, the removal is in the ratio of EP by V0 as ZP by Z0. This concept they have utilized in the design of primary sedimentation tank in water treatment as well as in wastewater treatment systems. Here I have just explained about the sedimentation basins. Okay, you can see here the water, the sedimentation basin have 4 zones. Okay, one is the inlet zone, another one is the outlet zone, then third one may be the sled zone, then fourth one may be the settling zone. Okay, the inlet zone, okay, it receives the wastewater through the baffle arrangement. Okay, it's like not a, it's a wall. Okay, with the provisions for opening. Okay, in between you have openings. That means they used to distribute the water uniformly into the primary sedimentation tank. Okay, in order to introduce the wastewater uniformly throughout the depth of the basin, they have constructed the baffle wall. The baffle wall have a provisions in the opening. Okay, these are the openings. Then water may enter into the inlet zone through this opening. Then in the next one is the outlet zone. The outlet zone, okay, the water will move forward in the upward direction, and then after the treatment with a sufficient retention time in the settling zone, then the water will move in the upward direction and then overflow over the weirs. Okay, that may be collected at the outer side. Then the sled zone, here you can expect the settling of the suspended impurities. It may be a discrete particle or it may be a suspended flocculent particles. Then the settling zone, okay, the settling zone, there only whatever the mechanisms I have explained. Okay, like some particle may reach the bottom of your sled zone, some particle may not reach the sled zone. Okay, then it may come out along with the water in the outlet. Therefore, the performance of the system depends on the settling velocity. Okay, now you can see that. Okay, this is the primary sedimentation tank. In the primary sedimentation tank, they have introduced the settling column. Whatever the concept we have studied previously. Okay, this is the settling zone. Okay, this portion is the settling zone. This portion is the settling zone. They have just imagined the settling column. Okay, initially the particle, because you are introducing the water to the inlet zone, therefore the particle may be at the inlet zone. Okay, this is the settling column, and then over a period of time, because it's a continuous flow, whatever things we have studied in the previous one is with the batch study. Batch study means there is no movement of the flow. That means there is no mass transfer across the system boundary. There is no inlet for the flow to the column. Okay, there is no outlet is there, but it is like a batch system. You are just keeping the water for certain time, then you are observing all those things. Whereas in continuous system, there is a continuous input to the unit and then there is an output. Okay, that is called as the continuous system, or we can say that there is a mass transfer across the system boundary. For example, this is the system. The primary sedimentation tank is the one treatment system. Okay, maybe you can draw an imaginary line. Okay, here you can expect there is a mass transfer from outside to the inside. Okay, you are receiving the flow from the sewer that may be admitted into the primary sedimentation tank. After the detention time, the flow may leave the tank at the opposite end, and then this is also continuous. Therefore, there is a mass transfer across the system boundary, that is called as continuous flow. Now, whatever things I have explained here is that is what we are saying now is with the continuous flow. Okay, you just consider only the settling zone. The settling zone, okay, then at time t equal to 0, then the column may be at the position, maybe you can see that this may be at the time at the initial point. Maybe over a period of time, because of the horizontal movement of the fluid, there is a movement of the column. Also, the particle will settle at the bottom. I will explain now. If can see that the discrete particles falling through the settling column will have now two components. One is the terminal settling velocity, already we have studied. Another one is the horizontal component. Okay, this component will not be there for the previous, that is for the batch study. But whereas for the continuous study, you have to consider the horizontal component. Is it clear, students?
Yes, ma'am.
Yeah. Now, in the continuous process or in the real treatment systems, okay, the particle that is in the settling zone may be subjected to two components. One is the terminal settling velocity. Another one is the horizontal flow velocity or velocity of flow through the settling zone. That is, as you all know that terminal settling velocity is related to the particle, that is equal to g into rho w minus rho p into dp square divided by 18 mu. Okay, then the horizontal velocity, that is vh, that is related to the flow, that is equal to q divided by cross sectional area. A is the cross sectional area of the chamber. Okay, then the sum of these velocities is the absolute velocity of the particle. Okay, by adding the terminal settling velocity and the horizontal flow velocity, will get the absolute velocity of the particle. Now, yeah, I will come to this point later. Yeah, before that, I want to explain this. Okay. Now, this is a continuous system. We are detaining the fluid for certain time period, that is called as T0. T0 is the detention time. Okay, the detention time or retention time, that is equal to volume divided by volume of the chamber divided by the flow rate. Okay, for this case, the volume of the chamber is L into Z0 because they have considered the height of the settling zone. Okay, Z0 is the height of the settling zone, that is equal to Z0 into W is the width of the chamber divided by the flow rate. Okay, this is one equation. Now, also you can consider the time of fall. The time of fall, that means time to reach the bottom. Okay, based on the average settling velocity that we have already discussed. Okay, that is equal to Z0 by V0. Is it clear, students? Instead of this is average, like the time of fall, T0 is, or I can say that the average settling velocity we have considered, no, based on the height of the column we have calculated distance travel divided by time of travel. Okay, the time of travel we can, it is like T0 is Z0 by V0. Okay, now you please remember this concept. Okay, for the particle to reach the bottom, that means the particle to reach the bottom of the settling zone, before the water leaves the tank, then the time of fall, okay, should be equal to the time of horizontal flow. Time of fall should be equal to the time of horizontal flow. Is it clear?
Yes, ma'am.
Yeah, please, this is important. Now, one T0 we have calculated based on the retention time. Okay, that is based on L into Z0 divided W divided by Q. And then T0, another T0 I have calculated based on the time of fall, that is based on the settling velocity of the terminal settling velocity. It is just average settling velocity. Average settling velocity. These two values to be or same, then only you can expect the particle to reach the bottom. Okay, therefore what we can say that, okay, these two things are same, then we can write this is equation 1, this is equation 2. You relate 1 and 2, then L Z0 W divided by Q is equal to Z0 by V0. Now you can cancel this value, then V0 is equal to Q divided by L into W. What is this? V0 is equal to Q divided by the surface area. That's why the depth is not considered as an important criteria in sedimentation basin. The velocity, average settling, that whatever things we are calculating is depends on the surface area of the chamber. Okay, therefore you have to remember that. Okay, then the depth is not an important criteria in the design of sedimentation tank. Is it clear?
Here we have nowhere incorporated terminal velocity.
No. Now what you have to do is, now you have V0. Now calculate the VT. If VT is greater than V0, it will settle the bottom completely. It will reach the bottom. That's why I have. Okay, yes. Now it is clear. Okay.
Yes.
Whatever thing I have calculated, this is based on the movement of the fluid average based on the height of the sedimentation basin or height of the settling zone. Okay. Now you know how to calculate V0. V0 is Q divided by the surface area of the chamber. That's why in the design, whatever things we have discussed yesterday is with overflow rate. In the problem statement itself, they have given the overflow rate or surface loading rate. How much amount of flow is applied over the surface area. Is it clear?
Yes, sir.
Now what you have to do is to find out the performance of the system. If the particles are having velocity greater than Vt, definitely will be removed. That means removed means it may settle at the bottom. If the Vt is less than V0, okay, that will also be removed if it enters at some other height. That's why here also they have explained this concept. There are two positions they have explained. Okay, if the particles with a velocity greater than V0 will reach the bottom of the settling zone, there is no doubt at all. Then if the particles having velocity less than V0 also to be removed. That's why they have shown this path. You can see this path. That means it is reaching the bottom of your sedimentation settling zone. Okay, but it may the height should be with the ZP. Then only it will reach the bottom. If it is with velocity less than that, definitely it will not reach the settling zone. It will go like this. That means the performance of the system is not good. You can expect some amount of suspended solids in the outlet. Is it clear, students?
Yes, ma'am.
These 3 points, whatever things I have explained today is, initially we have I have explained how to calculate the terminal settling velocity based on the density of the particle and the dynamic viscosity, and then that is actually that is a famous equation that is called the Stokes equation. Okay, to calculate the terminal settling velocity of the particle. Then I have explained about the settling column, type 1 settling column. Okay, because most of the primary sedimentation tank in water treatment system as well as in wastewater treatment systems, okay, they have based on designed based on type 1 settling. Type 2 settling is you cannot expect the path like this. Okay, that is a because here the straight line indicates that there is no change in the velocity, but type 2 settling is you can expect the variations in the settling velocity with respect to the time during the movement. Therefore, the path may be like a parabolic path like this. It will go like this. Therefore, we have to consider to calculate. That is a separate study that I don't want to explain to you. Okay, this is itself sufficient. You please understand that here I have explained the batch column. Okay, the same concept they have utilized in the continuous process. For the continuous process, you should know about what is the terminal settling velocity of the particle, what is the horizontal flow, and then based on this, okay, we can find out what is the detention time, because the detention time is related to the horizontal velocity. Okay, maybe by you can rearrange this equation that this is related to this. VH is related to the T0. Okay, length into length by what is T0. Also we can write T0 as L by what is T0 L by what is L by VH. No, I can write T0 as L by VH. Okay, this is one way you can write. Okay, anyway, this is not, don't confuse too much. And then next one I have explained about the detention time. I have explained about the time of fall. For the particle to reach the settling zone, the time of fall should be equal to the time of travel. Okay, then by equating these two, you may end up with the average, that is the average settling velocity, that is equal to Q by AS. Now do the calculation. If the VT is greater than V0, that should be completely removed. That means it reaches the settling zone. If the VT is less than V0, okay, that will also be removed completely. If it enters at the height ZP, if it is in between, that should be removed in the ratio of like what are things we have studied, VP by V0 and ZP by Z0 ratio. Okay, it will not remove completely, only on some fraction of portion may be removed. Okay, if the velocity is less than that, it may enter at some other height. Okay, these concepts you have to remember in the primary sedimentation tank. Okay, then yesterday I have explained about the weir loading rate. Mainly during the design calculations, we have to check it for weir loading rate. If the like weir loading rate is for example, it exceeds, I have given some values, what is that value I have given, the conditions. Weir loading rate for primary sedimentation basin. No one is opening your mouth. Students. Yesterday I have dictated, the weir loading rate should be 125 to 500 meter cube per meter per day. Then, for example, whatever the problem we have designed yesterday, it is coming around 378 meter cube per day per meter length of the weir. Okay, it is 378. It is less than that. Okay, then I have asked two questions. Okay, how to, for example, sometimes the width of the chamber is less than here it is 3.7. It is fine. Then sometimes if it exceeds 500, how do you reduce the weir loading rate? How do you reduce the weir loading rate? You have to increase the length of the weir. That means here we have placed the weir across the width of the chamber. Yes or no? The weir is across the width, that is equal to width of the chamber. In order to reduce the weir loading rate, then you have to increase the weir length. Have to increase the weir length. The weir to increase the weir length, we have to provide the weir arrangements like this. Okay, this is the width of the chamber. Near the outlet, maybe in the outlet zone, you have to provide one more weir. Okay, that means the flow is just entering into this. It is from the in the outlet zone. Okay, from the tank. Okay, just imagine you have to provide the like in the top portion, the top of your sedimentation basin, you have to provide a small channels like this. Initially, it may overflow like this. It is only at the end. Okay, instead of that, okay, in the outlet zone, you have to provide one more weir arrangements. Okay, that means initially it is W. Now it is entering into the system W plus W. Is it clear? This is called wear length. Now you can see here it is not only W. Okay, it is entering into this narrow channels from the like two sides. Therefore, for one channel alone, the wear length is W plus W. Then here you have one more provisions than W plus W. Is it clear?
Yes, ma'am.
Then four times. It is 4 times of W. Therefore, by doing this, definitely we can reduce the wear loading rate. Okay, the like some modifications in the arrangements at the outlet will control the wear loading rate. Here it is fine. It is satisfying the conditions. Then there is no issue at all. Then you can say that the design is safe. But sometimes if it exceeds, then you have to increase the wear length with this type of arrangements. Okay. Then I have given some problem now yesterday. How many of them completed? Amit Vikram. He is on hold. He is not attending the meeting. Yuvraj. Yuvraj is there. Satvika, Devi Satvika. Maybe. Satvika is there. Satvika. Sharon, you can note down the number, Sharon.
Yes, ma'am.
Bhavana. Bhavana. There is no response. Yeah. Have you completed the yesterday's homework?
No, ma'am. I tried.
What is the issue? What is the problem with the problem? No, what I have given some design. No, that you have to complete it. Anyone tried? Anyone tried? Okay, you just try to complete that problem. Anyway, I will ask maybe in the next class. Okay, you can note down the design of circular sedimentation tank. Please note down. Today I will just complete with the sedimentation portion. Then next class I will start with the biological process. Okay, you can take the municipal wastewater treatment plant. Processes an average flow of 5,000 metric cube per day. Average flow is 5,000 metric cube per day. Then with the peak flows as high as 12,500 metric cube per day. Then design a primary clarifier. Design a primary clarifier. To remove approximately 60% of suspended solids. At average flow. Then you have to tell me the steps, then I can proceed. Okay, here please note down the overflow rate corresponding to 60% suspended solids removal is equal to 35 meter cube per meter square per day. Okay, can you just tell me the procedure, how to find out the diameter of the tank? How to find out the surface? What is the first step? No one is opening your mouth. Students, you have to interact with me.
We have to find the surface area of the tank.
Yeah, we have to find out the surface area. Surface area of the clarifier. What is that difference between, have you heard of the term clariflocculator? What is clariflocculator? Maybe you have studied a flocculator, and then you have studied about sedimentation tank. If both operations are carried out in a single tank, that is called as clariflocculator. Okay, that generally we used to use in water treatment system. Okay, clariflocculator. Clarifier is the sedimentation basin. Okay, now what is the surface area? We have to design the system for average flow 5000, then divided by the surface overflow rate, that is 35. Then surface area is 1. (43 meters square). Then assume that you are going to provide a circular sedimentation tank. Then you can find out, based on the surface area, you can find out the diameter. Yeah. Babita is there? Babita Bisnoy. Babita. Sharon, you can note down. Babita is missing. Okay, she's not. Then Hashwant Patabi. Okay, a lot of people are not there. Anirudh Kumar is also on hold. Amit Vikram is on hold. Okay, you can just note down, these people are not attending the meeting. Others are also, I don't know, but you can note down. Sharon, send me the message afterwards. Abhishek is also on hold. Okay, maybe they are in another meeting. I don't know. Sami, Tula there?
Yes, ma'am.
Yeah, can you tell me what is the value of the diameter?
Wait, ma'am. I have to calculate. I haven't calculated.
No, I'm waiting. No, no, you have to do by yourself.
Yes, ma'am.
Yeah. Others, anyone tried for calculating the diameter of the tank?
13.5 meter.
13.5 meter.
13.4,
Okay.
ma'am.
Yeah. Then you can assume the depth of the basin as 3 meter. This 3 meter is for the settling zone. Okay. Then find out the volume of the tank. Then that is equal to area 143 maybe into 3, then this is equal to 429 meter cube. you can use this one to check for the detention time. Detention time is detention time at average flow. Then it is 429 divided by the flow rate. It is 5000. It is equal to 2.06 hours. You convert into hours. Okay, it is 2.06 hours. I think what is the design criteria I have given? It should be between 1.5 to 2.5 hours. No, it is like, yeah, 1.5 to 2.5 hours. Maybe it can handle the average flow with a retention time of 1.5 to 2.5 hours. If it is peak flow, then what will be the detention time? Detention time during peak flow, maybe during the rainy season. Then this should be values around 12,500. What is the answer in terms of hours? Students, this also you have to calculate. Then calculate the overflow rate.
It's coming 0.82 hours.
0.82.
82.
Less than 82 hours. Okay, this is less than 1 hour. Okay, then slightly the performance may come down during the peak flow. Okay, then overflow, but we have to be mostly we can expect only the average flow during the normal period of time. Then the overflow rate, we have to check it. The overflow rate at peak flow condition is 12,500 divided by the surface area as 143. What is the answer? 87 meter cube per meter square per day. What is the value they have suggested? It should be 100. Okay, it's 80 to 120. 80 to 120. Therefore, this is fine. Then how do you find out the wear loading rate? Wear should be provided circumference of the circular tank. Okay, the circumference is equal to the wear length here. Okay, that you have to calculate and then find out what is the wear loading rate. Is it clear, students? I can stop with this. Yeah, you just go through the content, and then next class we will study about the biological systems.